Keeper 6.5, net or total change. All right, so first thing we need to make sure we understand our units for our integral. So if I, for instance, was taking the integral of velocity and the velocity was measured in miles per hour, the integral would be the position function, which would be measured in just miles. All right, so the integral of velocity will just be whatever your position function is measured in, which in this case would be miles. Right now, if I was taking the integral of acceleration and it was in terms of meters per second squared, remember that the integral of acceleration would be velocity. And so velocity is still a rate. And so our integral of acceleration would simply be meters per second. All right, so our first example, it says at 7 a.m. water begins leaking from a tank at a rate of leaking equal to 2t plus 0.25 t gallons per hour. T is the number of hours after 7 a.m. How much water is lost between 9 a.m. and 11 a.m.? All right, so setting this up, I'm going to set up an integral, but I don't want to use 9 and 11. I want to use how many hours it is from 7. So I'm going to set up the integral from 2 to 4 because 9 a.m. would be 2 hours after 7 and 11 a.m. would be 4 hours after 7. So I have the integral from 2 to 4 of my function 2t plus 0.25 t dt. And then I'm just going to integrate that. So I get t squared plus t squared over 8 from 2 to 4. Or I could have added like terms and simplified it that way. All right, so anyway, I plug in my top and I get 4 squared plus 4 squared over 8. And then I plug in my bottom and subtract. So minus 2 squared minus 2 squared over 8. And I'm left with 16 plus 2 minus 4 minus a half, which gives me 13.5. So 13.5 gallons of water was lost between 9 a.m. and 11 a.m. All right, example 2 says the table given below represents the velocity of a particle at given values of t, where t is measured in minutes. Approximate the value of the integral from 0 to 30 v of t using the midpoint Riemann sum. Use correct units of measure, explain what this value actually represents. So using midpoint Riemann sum, and they didn't tell us how many subintervals, I think I'm just going to go with 3 subintervals, because if I do 3 subintervals, I can go from 0 to 10, and then 10 to 20, and then 20 to 30, leaving my midpoints as 5, 15, and 25. And so I want to pick something where I have nice even intervals if possible, to where I don't have to guess what the values are. So I'm going to use 3 subintervals so I can get midpoint values in there. All right, so the integral from 0 to 30 v of t dt approximately equals, again, using these intervals that I showed, each interval has length 10. And so that would be the base of my triangle. So I have 10 times, and then using the midpoint values of 1.6, 3.1, and 1.6, I could add that up to get 10 times 6.3, which is approximately 63 feet. Well, what does this mean? This is the amount of feet traveled by the particle from 0 to 30 minutes. All right, next example says, well, it's not the next example, it's still continued the same example, but part B says, what's the value of 5 to 25 a of t dt using correct units? Explain the value of this, of what it means. So we have the integral from 5 to 25 a to t, which we know that the integral of a of t, or acceleration, is just simply velocity. So all I'm really finding is the velocity from 5 to 25. And so that's going to be v of 25 minus 5, or v of 5. And v of 25, they told us, was 1.6. And v of 5 was 1.6. So our integral is approximately, or is equal to 0 feet per minute. Now, what does this mean? It represents the change in your velocity, or the amount of change in the velocity from 5 to 25 minutes. All right, so example 3, we have a cylindrical can of radius 10 millimeters is used to measure rainfall in Stormville. During the first 5 days of a 60-day period, 3 millimeters of rainfall has been collected. So the height of the water in the can is modeled by the function S, where S of t is measured in millimeters and t is measured in days from 5 to 60. The rate at which the height of the water is rising is given by the function s prime of t equals 2 sine 0.3t plus 1.5. So part A says find the value from 10 to 15 of s prime of t. All right, so the value of from 10 to 15 s prime of t, well, s prime of t, they told us is 2 sine 0.3t plus 1.5. So I'm simply going to take this function and I'm going to throw it in my calculator because this would be a calculated problem because of this 0.3t or this 0.03t. So I just throw that into my calculator and I get 11.159 millimeters. Now, there is a shortcut key in your calculator for plugging that integral in. You're simply going to do control plus sign, and that's going to give you that integral formula or that integral like template. All right, so once I get that in, I can say what the problem actually means. Well, again, that means your delta water level or your change in water level in millimeters from days 10 to 15. All right, so same exact example. This time they want to know how much water we accumulated in the 60-day period. So I'm going to set up an integral for this. Now, again, my mind is telling me since they want the whole 60-day period to do an integral from 0 to 60. However, I can't do that because the formula they gave us was only for t being between 5 and 60. So when I set up my integral, I'm going to do the integral from 5 to 60 of my function dt. Again, I'm going to throw this into my calculator and I get 163.565. Now, what that is telling me is how much rain was accumulated from day 5 to day 60. They wanted the whole period, though. So to do that, I have to figure out how much water was actually accumulated for the first 5 days. Well, if you go back up to your scenario, it says during the first 5 days, we had 3 millimeters of rainfall that was collected. So simply, I'll take my integral, I add on that starting amount, which is 3 millimeters, and I get 168.565 millimeters were accumulated in the 60-day period. All right, example 4 says the rate at which people enter an auditorium for a concert is modeled by the function R, given by, and they gave us the function from t going between 0 and 2. RT is measured in people per hour. VIP tickets were sold to 100 people who are already in the auditorium when the doors open at t equals 0 for general admission ticket holders to enter. The doors close and the concert begins at t equals 2. All right, so it says if all VIP ticket holders stayed for the start of the concert, how many people were in the auditorium when the concert began? So what I'm going to do is I'm going to set up an integral, and I have the integral of my R of t. And I went ahead and threw that in my calculator because the numbers look really big. And I just got 980 people. Now, again, I rounded that appropriately because I wanted to make sure I understood that I'm talking about people. All right, so I have 980 people from 0 to 2, but I have to remember that I already had 100 people chilling in the auditorium. They're already sitting in there. So I have that 980 people plus the 100 starting VIPs that were in the auditorium, which gives me 1,080 people in the auditorium. Okay, so back when we learned particle motion, we talked about finding displacement and total distance, and we had a little formula for how we were going to find displacement and total distance using the original position function. Now we can also find displacement and total distance using integrals. So to find displacement, you're simply going to do the integral from your starting to your ending point of the velocity of the function. But to find your total distance, you're going to do the integral of the absolute value of your velocity function from point A to point B. All right, so again, if you know the velocity function, all you have to do is integrate it, and you can find either displacement or total distance, and you're good to go. All right, so example 5 says, assume a particle moves along a straight line with given velocity. Find the total displacement and total distance over the time interval. So I'm giving you guys some function, and we're going from -5 to 5. So let's start with displacement. So for our displacement, we're going to do the integral from -5 to 5 of that function, x squared minus 2x minus 4 dx. Now integrating that function, we get x cubed over 3 minus x squared minus 4x from -5 to 5. Then I'm going to plug in the top of 5 minus the bottom. Simplifying that, I get 125 over 3 minus 25 minus 20 plus 125 over 3 plus 25 over 20. And then I simplify that to get 130 over 3. Now that would be like feet or meters. It just depends on what they tell you in the problem. This problem didn't tell us, so it's going to be like units. Now to find our total distance, we're going to do the same exact thing, except for this time I'm doing the absolute value of x squared minus 2x minus 4. And so when I plug that, or when I work that in, I'm going to use a calculator because I don't know how to yet find the integral of an absolute value function. So using that calculator, I get that the absolute value, or the integral from -5 to 5 of x squared minus 2x minus 4 in the absolute value signs, remember, is 74.148.